Okay, hello everyone. Welcome to another edition of our seminar. Today, very happy to have Susanna. Susanna had her PhD in Rome at Sapienza with Andrea Maselli. She's now a postdoc at UCD in Dublin, and she'll be telling us about testing GR with MRIS. So, Susanna, welcome.
Thank you very much, and thank you very much for the invitation. I'm very happy to be here. So yes, my seminar will be about testing GR with extreme mass resistance spirals, which has been, let's say, the focus of all my PhD and our work, which I'm still carrying on because I really like it and I think it's really interesting. And so extreme mass resistance spirals, I'm going to be, I think, a bit broad, so I'm sorry that you know already a lot of things. And if you have any questions that can be into technical in the other sense, please just ask, which I'll try to answer. Okay, so extreme mass resistance spirals are symmetric binary systems composed by two compass objects. We have a very massive black hole at the center, called the primary object, and then we have the secondary, which is a small compass object and spiraling around the primary until the plunge. Okay, so this kind of systems, the little guy completes thousands of cycles around the strong region of the primary object before the plunge, and by tracking the continuously emitted gravitational waves from this system with LISA, it's possible to build a very detailed map of the binary spacetime. So this kind of system emits gravitational waves in the millihertz frequency band, so they will be among the main target of the future space-based interferometry. And with this precise mapping of the space-time around the primary, we can see that it's possible to reconstruct the binary parameters with a very high accuracy. Okay, so all these characteristics make MRIs very promising sources to probe the space-time and the primary space-time. So one can think about MRIs as probes of the primary space-time, so that one can go and test, for example, the Kerr hypothesis, to test the nature of the primary black hole, and also to test the environments surrounding the primary object. What I will present here is, let's say, a shift in this paradigm in which the focus will be set on the secondary object. So when you want to test the spacetime around the primary, what you do is basically considering the perturbation of the spacetime of a modified spacetime. This can be really challenging. What I will present here is the focus is set on the secondary, and the perturbation are made just on the Kerr spacetime. So this is really simplify our description of extreme mass resistance spirals in this sense. And all the deviation from general relativity are given by the properties of the secondary object. So one can think of this in a very different ways. As for example, testing GR by considering new fundamental fields, or by considering this as an exotic compact object and testing the structure of the secondary object, and so on. So what I will focus here is considering this kind of system in modified gravity theories with new fundamental fields. So again, I want to stress that the perturbations here are done on a Kerr. Okay, so let's see the theoretical framework I will present. I'm considering a lot of vast class of modified gravity theories here, which are all described by this action here, which has a very general form. And I'm considering GR plus a new massless scalar field. So I'm focusing on shift symmetric theories. And we can see that the action here is composed by S0, which is just the Einstein-Hilbert term of the action plus the kinetic term for the scalar field. Then there is the coupling term of the action, and here we have the fundamental coupling constant of the theory, which has the dimension of a mass to the power of n. And then we have the action of the matter. So we can see that in this case, what happens is that if you have two black holes here, the scalar charge acquired by these black holes goes as this fundamental coupling constant over the mass to the power of n. So if we focus on Emrys, what you have is this supermassive black hole, which has this big M here, on the right here, and the little guy, which has the smaller mass. So basically, the more massive your black hole is, the less charged it is. And this allows us to consider just the scalar charge of the secondary object and to suppress the scalar charge of the primary one. What you have is basically just a curved black hole and a secondary object that carries its scalar charge, which we call here D as a dimensionless parameter. Okay, so let's focus on the secondary object. What is this scalar charge and how we are treating the action of the method fields? So basically, it's just simply replaced by the action of a point particle. So in GR, this will be just the mass of the particle integrated here. In this alternative gravity theory, what you have is that this one is a scalar function of your scalar field. And this is so what we are considering as the action of our secondary object. And you can see that we have two different turbulence scales, and we can consider the world tube around the secondary object. And if we put ourselves in a resonant frame centered on the secondary object, what we have for the scalar field is this expansion here, basically. So R tilde is the reference frame centered on the secondary object. And this is what we are calling the scalar charge. So it's not any charge associated to another current. It's just a parameter that appears here in the expansion of the scalar field. Okay, and this parameter here appears when one go and obtain the field equations. It appears in the field equation for the scalar field. So basically, what we can do is just treat all our system in perturbations, considering as the bookkeeping parameter the mass ratio. And by considering just the leading order in the mass ratio Q, one can consider the perturbation of your metric tensor and of your scalar field. And here I will present all the results that we obtained just at the leading order in the mass ratio Q. But I want to say that all of this has been put in a precise self-force scheme by a recent work by Andrew Spires at the University of Nottingham and collaborators. And in this work, they consider also the next order, the second order in the mass ratio Q, and the first order is given by this field equation that we obtained here. And even at the second order, what one obtains is that the background is still given by the kinematic, so you don't have any modification in this sense. You're always perturbing the kinematic. So these are the field equations that we obtained by buying the action with respect to the field, and we can see that this one is exactly the one that we have in GR. Okay, for the metric tensor. And then we have the field equation for our scalar field, which is a scalar wave equation with a source term. And this source term here is proportional to our scalar charge, which fully control the source that is sourcing this scalar wave equation. So then we can see that the leading order in the mass ratio, this field equation has a universal form because all the details of the underlying gravity theories that we are considering is just enclosed in this new extra parameter, which is the scalar charge of the secondary object. So now one can go and solve this equation with the Tucholsky approach, which is what we did, and I will present the results of this. Okay, so this is all the works that we have been done in this sense. As I mentioned, the second order perturbations have been developed in this recent work, and there is some implementation that we are trying to do and on which I'm focusing right now, which is in progress. Then we considered different type of orbits, so I will present the results here, and these works have been done in collaboration with other collaborators like PhD students Matteo Della Rocca at the University of Pisa and Sara Lior at the University at the GSS site in Latvia. Okay, so these are different types of orbits. We performed a parameter estimation of the binary system to see how LISA will be able to detect or measure the scalar charge carried by the secondary object. And I will present also those results. Okay. Okay, so our system is this Ambry system with a secondary charge, and by spiraling around the primary, this secondary object emits not only gravitational waves but also scalar waves. And these extra scalar waves,
So, hello again, we're back.
Welcome back.
okay, and
Sorry.
okay, so I was saying that we do not have only gravitational waves, but we have also scalar waves, and they cause an extra channel of energy emission. So this will modify the orbital evolution of the Ambry with respect to the GR1, and this will leave an imprint on the later gravitational waves. So the way we are going to detect the presence of the scalar charge is with the detection of the gravitational waves emitted by the Ambry to see if we can see this imprint left from by the scalar charge of the secondary. And at this order in demonstration, everything is very easy because you just need to compute this extra scalar energy emission, which is proportional to the scalar charge of the secondary object. This is simply added to the gravitational one, and then everything you built for the Ambry description, the gravitational wave emission, and everything else simply follows from free just by adding this extra scalar energy emission to everything that has been. So here I will present all the results in this procedure. I will show how to build the adiabatic orbital evolution of the Ambrys and some data analysis that have been done among the gravitational wave signals. Okay. So I will first focus on different type of orbits. Basically, what you do is that you solve and you compute your energy fluxes from your gravitational and scalar waves. So they contain both the gravitational and the scalar emission. And then you can impose this adiabatic leaf in which the orbital evolution is built as a sequence of geodesics. You can impose this balance law and consider this as the rate of change of your integral of motion associated to your geodesics. Okay, so these are some formulas for the equatorial eccentric in spiral, just for reference. From the rate of change of the integral of motion, you can go to the rate of change of the orbital parameters, for example, the semilatus rectum and the eccentricity of your orbit. And then from this, you can compute the phase evolution of your spiral, and then the dephasing by evolving a binary in the case in which you do not have the scalar charge, so GR, and in the case in the presence of the scalar. So this is a force quantity that you can compute to see if your scalar charge is bringing you possible detectable effect. And so this is what we've done. It's of course just a first hint because it's not rigorous at all, but it's nice to see, especially because we obtain very high values of the dephasing depending on some binary configuration. So for example, here I'm presenting the dephasing obtained in 1 year of evolution before the plunge. So for 1 year of observation around a spinning curve black hole for this kind of secondary mass as a function of the primary mass and the logarithm of the scalar charge. And we have in mind a threshold of resolution by ESA, which is this 0.1 radians. So basically, you can consider detectable a detectable effect like any dephasing higher than this 0.1 threshold. And this is true for signals with SNR of 30 is a first indication, and we will proceed in this sense also for the other analysis by having in mind a threshold for detectability. Okay.
Can I ask a question? So for the dissipation, you're just considering quadrupolar term or?
No, these are the policy fluxes.
I see.
So they have been computed for the circular case, for example, up to Lm equal 10. So you just compute all the modes for the policy fluxes until you want a certain accuracy on the one.
But it's still kind of point particle approximation, is that correct? But then you have extended object effect.
It's Theokolsky with a point particle, which means you consider your perturbation, these are your situation.
Yeah.
And this leads you to your perturbation, and from this you build your fluxes, which are given as a sum on the element. The quadrupolar would be just the R equal M equal 2 mode.
Right. So if I think about considering post-Newtonian approximation, I'll have effects like the spin-induced quadrupole, which is related to the extension in the size of the object, which comes at a higher order, it's Newtonian order than 2.5, which is the quadrupole. And that adds to the dephasing. So even if you wouldn't have a kind of a scalar halo, it would be something else, but an extended object, you would have that. So my question is, you are considering this dephasing here as compared to the case without scalar charge. But my question is, in the formalism you're considering, is this accurate? That is, would there be some extended object effects that would contribute to the dephasing, even if you would not have the scalar charge? Because you're considering the possibilities as an extended object, it could be an echo, so it could be even a black hole, say. The question is, you will have some dephasing due to other effects.
Yeah.
How they look at.
Yeah, I think that to answer this question, you will have to do the other thing. Start with the accurate model.
Yeah.
For example, for this, I would say that there have been studies, for example, on the spin of the secondary object. So this is what we can.
Yeah, exactly. And spinning just a quadrupole, say, for instance, and
Yeah, so for example, we are not considering the spin of the secondary object because it has been proved not to be detectable by LISA. So we are neglecting that. But yeah, I agree with you, and then you should, I think, consider all the effects. A more accurate model, I would say.
okay, so but just to make sure here, you don't have spins, say, for instance, of your small object. Okay.
Yeah, we are considering just the dephasing given by this scalar emission, and of course one would have a lot of dephasing contributed to the challenge to disentangle. Okay, so yeah, this is the first quantity that we computed, which is the accumulated dephasing. It's nice to see how we can go up to thousands of gradients. So this is not precisely telling us that LISA will be able to detect the presence of the scalar charge, because of course now one has to build the gravitational wave template. But having such a nice number is a nice indication of a possible detectable effect by LISA. So what we did then is to build the gravitational wave template. For a first study, this has been done with the quadrupolar approximation. So this will be just your strain. For eccentric equatorial orbits, this is given by a sum of harmonics. And one takes into consideration the Lisa-Panther function and the different the amplitudes for each harmonics. They depend on some coefficients, which are given basically by the frequency, the luminosity distance of your secondary object. And you can build your template like this, as we did. And another quantity you can compute for a more quantitative estimate on the detectability of the scalar charge is the faithfulness. So this is a quantity that can tell you how two gravitational waves are different, and they are not compatible, let's say. And this is computed as the inner product between two different gravitational wave templates. So we consider one in the presence of the scalar charge and one in the absence of the scalar charge. You have your template as a time function of time. You Fourier transform it, you have it in the frequency domain, and you compute this inner product in which you weight it with the strain of LISA. And this is what we obtain for the faithfulness as a function of the scalar charge D. And here again we have a threshold for the LISA resolution. So basically all the dots obtained below this threshold here are considered to lead to a possible detectable effect. So the threshold is this one for signal of an SNR of 30. And we can see that for these values of the scalar charge, we obtained values of the faithfulness which are well below the threshold of detectability. And this has been done both for an eccentric spiral and for a circular spiral. And we can see that for the eccentric one, we obtain the values which are below the circular one. So this could mean that the eccentricity will enhance the effect carried by the scalar charge. Of course, by decreasing too much the value of the scalar charge, one obtain that the signals are not distinguishable anymore. So this could be an indication of the smallest scalar charge that could be detectable by LISA.
Can I ask another question? You're always assuming a curve background.
Yes.
But you're assuming you know exactly pass at the speed of background, and so you're making a comparison for the same background, right? So.
Yes.
But let's imagine, as it is always the case, we don't know, say, the speed. There's some error. So, is there a possibility of mistaking? So the different number of cycles, because with the uncertainty in the spin. So is there a degeneracy there? So will I get a similar result with a different spin, but still an object without scalar charge? As you see my question, right?
Yes. I see your question. I think that all these relationship between the parameters and the bias, everything is well more done with a proper bias analysis that we did.
Okay.
So these are the first steps, and I get that. And in that case, you can see all the posterior distribution on your parameters and the bias that you can obtain on the.
So you get what's most likely at the end of the day. If it's most likely that it's a different spin of the background, or if it is a scalar charge.
Yes. Yeah. Okay, so this is the faithfulness for spherical inclined orbit. same things. You can see this in quantitative behavior. We consider different inclination of the orbit around your primary object. The continuous one here is the equatorial prograde orbit, and it's nice to see that by increasing the inclination, the faithfulness decreases, and then you get retrograde. So the highest values here are obtained for the retrograde equatorial case. This is just some analysis for the orbit, but more or less the message is the same in the sense that these values of B could lead to a possible detectable effect for LISA. Okay, now let's go to the proper parameter estimation. What we did is first artificial information metrics as a first work, but now we have also the results with a fully Bayesian analysis done with the Markov chain Monte Carlo stochastic sampling, and I will present just these results as they are more rigorous and more accurate of what we have. In the Bayesian analysis, basically you want to recover the posterior on your parameters describing your gravitational waves. So I'm sorry, here there are a lot of these, but these are the probability distribution of your parameters given the data. So this is the data. Which are obtained with the bias theorem, with the light load, and the bias on your parameter. This can be considered as simply normalization constant. Okay, and so what we did is the Bayesian analysis with all these 13 waveform parameters. These are all the parameters that describe our waveform. So basically we have the masses of your binary, the primary spin, the luminosity distance, these angles identify your source in the sky, and then there are the initial orbital parameters and the scalar charge. Okay, this has been done not with the quadrupolar analytic template I've shown you before, but with fast-time waveform, which is a LISA pipeline, which is public, and one can just go and produce its own fast-time waveforms. And here, these are the fully relativistic default key waveform. Right now, it's open for the 0K level, eccentric Schwarzschild, for the eccentric Schwarzschild case, the fully relativistic one. So this one is the analytic, augmented analytic clutch models, which basically takes the fully relativistic trajectory, like completed with the fully relativistic classes, but then the amplitudes are built in this analytic clutch model. And actually, there has been a recent work published here that did this analysis with the Kerr circular fully relativistic, and I think for a few fast-time waveform, there will be also soon the release with the fully relativistic Kerr eccentric model. Here, in our analysis, the trajectory is fully relativistic, the amplitudes, the waveform with this AK model. And this has been done for equatorial eccentric spiral around the spinning the primary level. So these are the bounds that we obtain on the scalar charge by considering different types of binary systems. So these are the different injected values in the simulation of the data. And these are the forecasts that one can, on the upper bounds that one can obtain. So here on the epsilon axis, you have the histograms for each kind of binary considered, and on the x-axis there is the scalar charge, and the vertical lines here means the 95% credible interval of your upper bound. So basically, this is telling you that we are injecting signals with d equals 0, and we are recovering the posterior on our scalar charge. So this is the upper bound that you can set on your scalar charge D. It's nice to compare the results that we obtain. We can take as a system of reference this number 6, and we can see that by, for example, decreasing the spin, which is this system number 5, we obtain a slightly worse bound, and by the same by reducing the eccentricity. So higher spin and higher eccentricity will lead you to tighter bounds on your scalar charge. The best bound that we obtain is for this system here. And has been done for just 0.5 years of evolution before plunge for the smaller primary object that we consider. And we have obtained best bound for this system because in this case, your secondary object is starting the spiral in the more weak field region. So it's mapping also it's more far away from the central black hole with respect to the other systems, and this will enhance likely your upper bound that you can set on the scalar charge, because in this region the scalar field emission is contributes more with respect to the closer region to the central black hole. So it's the dipolar emission that is dominant, and it's more high on that part. Okay, so these are our results.
To clarify one thing, so the capital M is the mass of the curved black hole.
Yes.
The one, and the little mu is the mass of the secondary. So we are talking about solar mass type of objects here.
Yeah.
Okay, and how about, but then the argument is that these scalar charges are diluted for large masses. I mean, initially you get kind of that argument. So even if you have a model, in which all black holes will scalarize, and it's more important for the small ones. Yeah. But here we are in the LIGO kind of range. So wouldn't there be constraints for the small one that it's so we are talking about 10 solar masses, something like that. So this one is truly scalarized here, right?
Yes.
So wouldn't this impact on LIGO observations?
But here you are in spiraling around a supermassive object.
Right.
So your waves is.
I understand. Well, what I'm thinking is, let's imagine that indeed the system would be in the universe and there's black hole with 10 solar masses that's scalarized, right? We've seen mergers of 10, 20, 30.
Yeah. So for there has been some bounds that are given from the current observation, for example, on Gauss-Bonnet, and I will compare their results with what we are obtaining here. So that has been done with the current observation on those systems which are more comparable masses. So for example, the best bound they can obtain is given by a system which is a neutron star, so Gauss-Bonnet is not charged, and on the whole.
But there you're talking about spontaneous scalarization, or are we talking about, say, dilaton coupling so that everything scalarizes?
Yeah, even that.
Because those models have also constraints from cosmology, right? So because of this GW 170817 yeah, but we can perhaps go to this more general kind of discussion at the end, and now you can.
Okay, so let's go on. So those are the bounds we were injecting GR. The actual measurement has been also tried, so we recovered the error that Lisa will be set on a specific value of the scalar charge. So we injected with the scalar charge, and we recovered with the scalar charge for this value here, and these are the errors at the 90% interval that we have obtained. So this is basically more or less a relative error of 20%. Okay, on the measurability, and then okay, this is are the biases in which now we injected a value of the scalar charge and we recovered with GR. So basically, we are assuming which are the biases that I obtain if in the universe there is this scalar charge by I'm just having GR, and what we obtain is that there are systematic bias at the order of 2-3 sigma on the intrinsic parameters. And this means that, for example, since you can obtain the errors on your intrinsic parameter in very high accuracy, this won't affect your astrophysical conclusion. Okay, because the errors on the masses or on the spin are so low that this systematic bias won't affect your astrophysical conclusion, but of course they will be problematic for a very small deviation, like for example beyond GR correction. And last thing is of this analysis is the mapping between our theory agnostic framework and the bounds on these new extra parameters to a specific theory. And for example, if we are considering a specific coupling time reaction here, which is scalar Gauss-Bonnet, we consider this specific expression for the coupling term of the action, and we can find a mapping between your fundamental coupling constants of the theory and the scalar charge. So from this, one can recover the upper bounds on the fundamental coupling constant of the theory. And here, so please, one thing is that note that this also depends on the value of the secondary mass. So for example, here in our theory agnostic framework, the best bound was given by system 1, while here it's translated to a better bound on the system 2 because of a smaller secondary mass of the system, yes. And here there are two lines. This continuous line is are the forecast from LTK Voyager, and they set the bounds to be here. So, but then a new event came out from the gravitational wave observation, which is this event here, which is a very particular event. Because there is a neutron star and a black hole which has a mass of around 3.6 solar masses. So this is a black hole in the low mass gap. Yes, for the masses of the black holes. So this is a very particular event, and with this event they set the most stringent bound on the coupling constant that we have up to date for Gauss-Bonnet. So we can see that our analysis for just these binaries that we have considered might lead to same order of magnitude bounds with respect to the ground-based detections, or slightly better. But one thing to keep in mind is that we are just considering some particular binaries. So what we will need at this point is a very a wide exploration of the parameter space and on Liandri systems to see which could be the golden binaries which could actually lead us to the tightest bound, let's say both on D and then on some specific theories as this one. Okay, so I'm going to finish. I don't know what time is it. Okay. I can finish by presenting the results that we obtained now with no-shift symmetric theories, in which, in this case, we consider also a scalar field with a mass. So we have that our action is simply changed by considering the mass term for the scalar field. And everything else is basically more or less the same, except that your field equation now for the scalar field is this one, and the mass appears on the left hand side of the equation. So basically now you have two extra parameters, which are the scalar charge and the scalar field mass. And we started with what, which is the effect of having also this the mass of the scalar field. So we computed again the Kolsky fluxes, and here they are plotted as a function of the orbital radius. So the continuous line is the massless case that we obtained, and we saw what happens by increasing the scalar field mass. And we can see different effects. So first of all, the total emission is decreased. It's a particular radius and you increase the mass. For your scalar field, your emission is decreasing. Also, we have to notice that for the here we are computing both the emission at infinity and the one that falls into the black hole. And for the emission at infinity, for each mode, this is decomposed in L and M modes, and for each mode, you can find a certain radius after which your emission at infinity vanishes. And here you can see it by looking at here is the total emission. Now, for example, if you go to these values of the scalar field mass, which is the inset here, you can see that the emission at infinity is suppressed. And you only have the emission at the horizon, which for this kind of spin is super radiant, so it means it's negative, so that's why it's going down. You have this shape of the scalar flux. And this each radius is different for each L and M. So this is the first effect. For what concerns the scalar energy emission at the horizon, that is always present. So the suppression of the emission at infinity is due to the potential barrier that comes from the mass of the scalar field. For the horizon, you don't have that, so you always have the emission into your primary black hole. What happens is that you can hit some resonances. So basically, you can have a very high scalar flux, and these resonances could cancel out your gravitational emission. So you can find yourself something like this, which means what is known as floating orbits, because now your total emission is zero, so basically your orbit is not emitting anymore and will stay there in that floating orbits. Here we are neglecting all the resonances for the emission at the horizon, so we are not considering any resonances or the floating orbits, the floating orbits effect.
Can I just ask to understand a bit better this model? So is the field by coupling? Because there's these other terms, which I'm not sure what they are, yes. So is this coupling in some other way to the curvature, or is it just considering that explicit action that you see there?
So this is, the kinetic term and the mass of the scalar field. And so here, this is just the coupling term, the nominal coupling between the gravitational and the scalar field. So we don't consider, we haven't put any specific expression.
But you're assuming there is one or not?
Yes, yes.
Yeah, that there is one?
Yes.
Okay. So that's why the small black hole is getting scalarized. It's because of that.
Yeah.
Because if it would only be that model, there would be no reason for it to scalarize except for radius. And actually, the values that you're considering that bar mu is given there. So you're considering constant wavelength of the order of the short radius of the big black hole.
Yes.
Not of the small one. So actually, the one that would scalarize by sporadics, even because the small one is not spinning, it's only the background one.
Yeah.
Because it's a real field, then you have possibility that this would be, I think, this continuous emission due to some clouds around it, right? But you're assuming it's the small one that's kind of scalarized because of the non-minimal coupling that's also there.
Yes.
Oh, then I understand.
Thank you. Yeah, and we are considering this, and we will considering, so this one, basically, yes, small or equal to one, this order of for the scalar field. So I mean, it's the line scale of your memory, and so these are the values of the scalar field mass that we are considering, and okay, so we computed the faithfulness also in this case. As a per quantity, and here it's plotted against the adimensional scalar field mass of your scalar field. Here there is the translation to electron volt to have a physical meaning of your scalar field mass. And in the upper panel, it is a comparison between the GR case, so both the scalar charge and the scalar field mass equal to 0 with respect to the massive case, so both set different from 0. We consider different values of the scalar charge, two different values of the secondary mass, and we can see that we obtained detectable effects, so low values of the faithfulness for all these values of the scalar field mass. And then, of course, by increasing the values of the scalar field mass, the energy emission is suppressed, and so you cannot see any more differences between the DGI. This is what happens. In the lower panel, we investigated a bit the difference between the massless and the massive case. So here, in both templates, the scalar charge is not 0, it's different from 0. In one case, the scalar field mass is 0, and in the other one, it's not. So as expected for very small values of the scalar charge, let's say to investigate which is the smallest values of the scalar field mass, which could be detectable from the massless case. So this is what we obtain. And here in the middle there is this band, which is the experience stability band for this particular black hole that primary black hole that we are considering. So a supermassive of 10 to the power of 6, a primary spin 0.9, and these values of the scalar field mass will increase superradiance instability of the primary object. And finally, we performed a Fisher information matrix analysis on these systems. So as the one done for the mapped case, which I have not shown because we have the Bayesian results. Yeah, we performed this Fisher analysis, and basically you can build your waveform as we did with these different parameters, and you can recover the errors on your parameters by computing Fisher information matrix. So basically, this is based on the fact that a larger scenario you can consider your posterior on your parameters as proportional to here that there is the prior and your Fisher information matrix with the product of the errors on the parameters. So basically, you build your Fisher information matrix, which is just given with the inner product of the derivative of your change state with respect to the parameters that you are considering. And once you build your Fisher information matrix, you invert it, and from the inversion of it, you can recover the errors on the specific parameters. And this is what we have done. For the scalar emission, we only consider the dipole scalar emission for computational reasons, because here you have, for the Fisher studies, you have to sample on all your, to compute all your fluxes in all the, for all your parameters with much more points, because you need to compute these numerical derivatives. For example, for a given spin, you actually need to stay in the interval between in the parameter. So just for a computational reason, we just consider the bipolar scalar emission of this study, and we computed several Fisher information matrices to recover the errors on the different parameters for different binary configurations. And here I'm presenting the credible intervals that we obtain specifically for the scalar field mass and charge for the different binaries that we considered by changing the values of the secondary masses. So different colors are for different values of the secondary, while the primary is fixed to a given spin and mass. And this is on the right side, there are the probability distribution marginalized for the single parameters with the white shader, which is indicating the 90% probability distribution. So from the table, you can see the relative errors that we obtain on the parameters. So for example, for the smallest case, 1.4 solar masses, basically you cannot constrain anything. These are the relative errors that you obtain. But what happens is that by increasing a bit the secondary mass, for two values of injected values of the scalar field mass, you can see that, for example, for these binaries here, you can obtain relative errors on the two parameters which are less or at the order of 50%. And this will mean a possible simultaneous simultaneous detection for LISA for both the scalar field mass and the scalar field charge. So this makes MRIs also promising candidates for the detection of ultralight scalar fields that we are considering here. These values here, sorry, I haven't said that 0.018 is at the order of 10 to the power of minus 18 electron volts. So we are considering ultralight scalar field. Okay, so this is all the work done. These are basically just the summary of what I've presented. As I said, it will be very nice, first of all, to explore the parameter space, I think, for these kind of binaries, especially to investigate which kind of binary configurations and also years of evolution of region around the primary object will lead you to the tightest bounds on the scalar charge and on specific ways. It will be nice also to start to think about sample adiabatic correction, to consider fully generic orbits, and for example also environmental effects and other effects that can enter in our description. Right now, I'm currently working to the inclusion of some post-adiabatic terms, especially with Andrew Spires at the University of Nottingham and other collaborators. As another project that we have in mind is to build a parallel pipeline for the generation of ML waveform in modified gravity theories, and I think this will be like our modified ML waveform pipeline, and there is currently a PhD student at the Grand Sasso Science Institute of Andrea Maselli, which is working on I'm working with her on generic orbits around the primary, and I would say that's it. Thank you very much for your.
So, do we have any questions for Susanna?
I can ask a further question.
Let's see if there's any on Zoom.
Yeah, no.
So, do we have any question over on Zoom?
Yes, I have one question.
Okay, yeah, go ahead.
Thank you. First of all, thank you for the very nice and very interesting talk. I saw that in the list of things to do, there was there was one on environmental effects. So I was wondering if there is a current work that has been done in this direction, or if there are any estimations, even rough estimations of how big these effects would be with respect to those that are predicted in your nice work.
Okay, so for what I know, so I'm not currently working on any environmental effect added to the presence of the scalar charge. There are very nice work which is separated by this. Studies on environmental effects, effect beyond GR around the primary, and all of these. And there is, I'm not currently working, and I don't think that there is a work that is putting these together. I think it would be nice. But for example, also working with Lorenzo Speri that worked both on the Bayesian analysis for in our case, and also with some environmental studies. I think this will be like the effect on the frequency of your gravitational waves, on your emitted gravitational waves, will be different. So you could be able to disentangle the two effects. I think it would be nice to see properly and to have a proper model, maybe to take into account both effects and to see how they interact. What I think, what we saw with some preliminary studies, and then we left it there, is that yes, they should be different effects. So you should be able to. Yeah.
So even qualitatively different, no? If that's the case, then it would be easier to make a distinction.
Yeah.
I see. Thank you very much.
Thank you.
Thanks, Hector. Any other question over Zoom? Okay, I'll take it as a no. Carlos, do you want to ask your question?
I could, it was just kind of missing a little bit of discussion earlier for, some of these models, they have, a scalar field that is always sourced by curvature, like, the model we just apply Gauss-Bonnet coupling that you showed there. And some of these scalar tensor models were heavily constrained by GW700817 because of the velocity. The problem is that the scalar field is sourced in cosmological distances as well by curvature, unlike models of spontaneous scalarization, where in principle you could only scalarize around compact objects. And this affects the velocity of gravitational waves. And over cosmological distances, even if this is a very small difference, it affects, and because we have a very tight constraint from GW700817, the coupling in some of these models is constrained to be extremely small. So I was wondering, how this affects, your considerations, because in that case, we have already very, very tight constraint on the coupling between, the alpha that is coupling to the gospel in. So I don't know if you thought about this, or if it has been.
But
maybe
this
looked at.
specific constraint, you are referring to Gauss-Bonnet or other theories?
I mean, so in the wake of this GW7070, there was a series of works that constrained a bunch of theories, in particular some scalar tensor theories, including within this family. As long as the scalar field is excited over cosmological distance, which is always the case with this type of model. But not with ones of spontaneous scalarization, where you only scalarize around compact objects. You see, there's a kind of, but in the model, say with a atomic coupling or a phi coupling, the equation of motion is just box of phi equals Gauss-Bonnet. So it's, space, it's cosmological, FRW, whatever. So then there is a little bit of scalar field, and this affects. It can be tiny, and people have calculated it. So, I feel sometimes there is these kind of non-talkative communities, one that looks more at cosmology and another one that looks more into compact objects. And, sometimes the constraints are not important. And, but I've seen, and actually I've got criticisms from referees about this. And I think it's something that in some of these models must be taken into account. So I was wondering if you thought about this or not.
For example, I might be wrong. I don't know if you're. I have in mind, for example, some constraint that comes from the GW70, which is, for example, the tightest constraint that comes for the uncultured assignment, for example.
Mm-hmm.
And this is very tight. Here, what we can do, what we did is to see our bounds for the specific theory of Gauss-Bonnet, and I think that what is nice is the theory agnostic power of the formalist. Because, for example, then if you want to go to specific theory, for example, to dynamical shell Simon, I'm not sure how the mapping would be between D and alpha, and I'm not sure I was interested into this. I haven't found if there is a specific mapping of how the mapping will be done. And so, yeah, this is a specific theory that we took into consideration, and we compared with the tightest bound that is for Gauss-Bonnet, and that is coming from the ground-based reduction of gravitational waves. So I think that, it's nice to see the different bounds that arise from different scenarios on the different theories and compare them. What we did is just considering the Gauss-Bonnet as a specific one. Yeah.
Yeah, I think in this case it's the alpha that is in front, so this is length square, right? And it was constrained to be something like 10 to the minus 10 or something like that, which is really, really small. So, yeah, but if you'd like, I can send you some references about this, and you can.
I think this is probably a good time to stop. Let's sign once again. And that's it for today. I'm not sure when the next seminar will be, but there will be an email.